This is the Ben C Gerwick Award presentation. My name is Rick Ellman. I am the chair of the DFI Marine Foundations Committee. And one of the committee activities that we have been doing since 2008 has been selecting innovators in the Marine Foundation world and similarly related construction activities, and seeking these people out and presenting this Ben C Gerwick Award in the honor of Ben, who was quite an innovator himself. Told you the award was originated in 2008, intended to recognize Ben C Gerwick's innovative spirit, his phenomenal contribution to the Marine Foundation industry over his 62-year professional career as a contractor, educator, and construction engineer. And it's also to recognizing and encouraging innovation in the Marine Foundations industry. The award is selected based on the following criteria that the Marine Foundations Committee established, which has been impact and value on the Marine Foundation industry, level of innovative nature, and relevance beyond the Marine Foundation industry. The award is sponsored by the DFI Educational Trust, years ago associated with the University of California and the Ben C Gerwick Company, but primarily now is a connection with the DFI Trust. So the DFI Educational Trust mission statement is to support and encourage students in the fields of studies related to the deep foundations industry by providing scholarships and opportunities to meet and work with deep foundation industry leaders. The goals of the trust are to provide financial assistance, to promote awareness, and to provide financial support, all with the aims of getting, students involved in the deep foundation industry. There's a myriad of scholarships that the DFI Trust sponsors, and these are all intended to develop funding for student scholarships. Right now, the trust holds $3.6 million in assets, has awarded $1.1 million in scholarships, and there are over 250 college students that can participate in this event. Future fundraising events will be the DFI golf outing in July in Pittsburgh, Pennsylvania. In August, the ACE Mentor Program Educational Trust golf outing in Hillsborough, New Jersey, and in October, DFI Trust annual California golf outing. So those are opportunities for anybody who's interested in participating. There will also be an inaugural DFI Educational Trust 5K run walk in October 16th, and then the Hal Hunt Lecture on Communications at DFI Annual Conference. The speaker will be Linda Alvarado, and that's October 17th. November 9th will be a gala fundraising in New York at the Terrace on the Park. Okay, so at this time, I will introduce our award recipients. So this year's award recipients for the Ben C Gerwick Innovation Award are Robert Mast, Arthur Anderson, who's receiving the award posthumously, and Thomas Anderson. And if Robert would mind joining us up on the stage. So these three gentlemen have been involved in innovations in the precast, pre-stressed concrete industry for decades and decades. And Lee will be giving a discussion about the award, but at this time I would like to present the DFI Ben C Gerwick Award to Robert Mast for his contributions to the precast concrete industry. Thank you, Robert. Yeah, okay, so let's take Tim. You want to take your hand before you go.
Am I coming through okay?
You want to take a quick picture?
Yeah, sure.
All right, step back.
I'm going to take 60 years and condense it to about 10 minutes. And thereafter, Lee, our president, will continue with me for the time. When I was 24, I had finished college and the Army, and I needed a job. I had heard of two brothers in a faraway place called Washington State. I'd never been within 1,000 miles of them. But I decided to find out about what the brothers were doing about a new thing called pre-stressed concrete. It wasn't in my university finds. The 5 years I spent, never heard of it. So I came to January 1959, met the brothers Art and Tom Anderson, and I managed to get a job with them. I planned to stay there 2 years, learn all I could, and move on. But I never stopped learning new things from them, so I never left. Things happened in the very first 2 or 3 years of my career there that were just so exciting. 1961, we were preparing for the new in 62, we had a World's Fair. And among other things, monorail was to be made. And we made it with pre-stressed concrete. That a lot of people said you couldn't do a pre-stressing on a curved beam. But I can say that now it's 58 or so years, and that's still working. So no problem there. I never stopped learning, so I never left. And that's where I am here 60 years later. I went with Art Anderson to San Francisco probably in the late 60s. And at that time, Art Anderson introduced Ben Gerwick, I should say, to me. And I never left or never thought of anything other than I knew it was a person that was very important that I wanted to be with more, as well as the Andersons. In the early 60s, we also developed a 48-inch diameter hollow that was a foundation and a superstructure all in one piece. Others had done this, so that was not a new idea. But we thought we had a better idea, which was to use a moving inner form to be able to make and finish a column and foundation in one unit in one day. And we were doing 3 or 4 a day at a time back in 61 or 2. And many of these structures were used in the interstate that was being built at that time. Subsequently, Ben and I were involved in quite a number of different things. Probably one of the biggest ones, was working on the foundation and superstructure of the Hibernia thing was built in Canada, floated out into the North Atlantic, and sat on the bottom about 200 feet below the surface, and was designed to resist the impact of the biggest earthquake, the biggest iceberg that could be reasonably done. And Ben set up a series of things to do over a period of 3 or 4 years. We had meetings in Europe, Oslo and Paris, for about a week every 3 or 4 years, or either 3 or 4 months, and give our ideas of what was going on and was it proper. And that was very good, very interesting for me. One of the later things I did with Ben was here locally after the Nisqually earthquake in about 18 years ago now. And what should we do with the double deck that was built in the early 1950s? And at that time, people didn't really realize how much we were at risk for earthquake. We always thought California was, but not here. But we were wrong. Working with Ben and others, we decided that we have to do something to replace the 50-some-year-old structure. It was just not feasible to fix it up. We didn't decide, or even we just noticed or said that we're going to need either a new superstructure or a new tunnel. And of course, others later decided that, and the tunnel is just very recently opened. We told that we should get that done in 10 years. Well, it took closer to 20 years. But that was finally done. It just took longer. The thing I'd like to leave with you is that I believe that Ben Gerwick was a wonderful man, every bit as wonderful as my previous men, Art and Tom Anderson. And I am thankful for the rest of my life to have been with those people. Thank you.
Okay. At this time, we're going to have Lee Marsh give a little more background to the honorees and their history. Thanks, Lee.
Thank you, Rick, and thank you, Bob. I'm going to cover some of those same 60 years here in sort of a pictorial form that I think you'll find interesting. Let's start with the photos of the three honorees here. And you can see Bob on the far right there. Looks pretty much the same today, I would say. Still a young guy, spry as ever. But the interesting thing here is these were all fine engineers, but they were also, all three of them were sons of contractors. And so that gave this story a bit of a backstory in the sense of we've always tried as a firm, as a design firm, ABAM engineers that you may be aware of, BergerABAM, and now more recently with WSP, but build structures that are constructible. And you'll see that theme through this presentation. So Art Anderson grew up in Tacoma, but ended up getting his doctorate at MIT under the person, the engineer that invented the electric strain gauge, and arguably from a structural engineer's perspective, the one invention, even over the computer, that I would say has given us a window into behavior of structures. And so he was there. He invented the Anderson strain meter that's shown here. So early data acquisition system. Many of you have been in the lab, you've fiddled around with this kind of stuff, you know what they can do. But in the late 40s, there was a project in Philadelphia of a new bridge overcrossing, and one of the firms that bid on it, Preload out of the UK, bid a pre-stressed concrete bridge. And City of Philadelphia said, that's not in the code, we don't know how that works, so you've got to do a full-scale test. And so Art was hired to do the instrumentation of this. And many of the famous names, T.Y. Lin and others, in pre-stressed concrete were involved in this test. It was successful, showed what you could carry with pre-stressed girders. And today when you drive around Washington State, you see many, many of these. But this was Art's first encounter with pre-stressed concrete and came back to Washington, started a firm. And he started Concrete Engineering Company with his brother, Tom, in 1951, down on the Tacoma Tide Flats. Interestingly, they were going to build a plant in Seattle. Seattle said, well, it's not in the building code, so you can't build that here. And so Tacoma said, well, you guys are the engineers, you do it. And so they founded Concrete Engineering Company, later known today as Concrete Technology Corporation. But a year later, they spun off an engineering company, Anderson and Anderson. And a few years later, Hal Birkeland, another one of the giant principals in this, joined the consultancy, and then Bob Mast joined in 1959. And they had enough letters in for a name, had two vowels that really worked well, ABAM Engineers. From there, as they were applying this new material, Art was always the showman. He's like, people would ask if you could do this. He'd say, well, let's ask the beam. Let's ask the concrete. So he'd build these things in the plant, instrument them, and show that indeed they would work. A number of the innovations you've seen, and this is a little broader than just marine foundations, but wide flange beams that are the WashDOT standard shapes now, and many other DOTs have adopted them, were developed by these guys. The double T's, the deck bulb T's, And Bob mentioned curved post-tension beams. I'll talk a little bit more about that in just a minute. Piles, pre-stressed concrete piles, hollow piles, and even an innovative technique, as Bob mentioned, for fabricating those. And then importantly, these guys were focused on the entire system. And I think that's something that really bears a lot of credit, deserves a lot of credit, is looking at the entire system of how this stuff works, not just the foundation, not just the substructure, not just the superstructure. So they started by building a plant. They built their own pre-stressed building. This is a pre-stressed concrete moment frame, basically. You look at the cars, I think it's early 1970s, but the plant was built in 52. The building's still there, and many of the products you might know around Washington State were fabricated there. One of the early things they did was the deck bulb T, came up with that concept. These were, as you can see here, fabricated with a curb and the diaphragms all included. Some of the early uses of pre-stressed beams were on logging roads in the Cascades. Actually, these beams were quite a bit less valuable than large diameter old growth logs. And so the Forest Service and timber companies were very interested in using these. Then enter pre-stressed concrete piling. This was an idea that certainly relevant here in terms of marine foundations. A lot of people said this would not work, that if you pre-stress the pile when you drove it, you would destroy the concrete. Art was like, well, you know, you've seen this little Newton's cradle device where the clackers go back and forth. So he knew he had to reinforce for the reflective wave off the bottom of the pile, but he knew that it would work. And they built a line to build these things, and there are more pre-stressed concrete piles around here than you can count. They indeed do work. Here was one of the early pre-stressed concrete systems. I've heard it called the Pacific Northwest Pier System. Compare in California, where it's mostly cast-in-place superstructure. This is pre-stressed concrete piling with precast deck panels. And you see the haunch deck panels that were quite efficient within a cast-in-place cap. Still using this kind of construction. It's evolved a bit to be sturdy enough for seismic loading. We don't use the batter piles anymore, but the system's still around. Some bridges. This is the Day Island Bridge, 1958. You see the piles are pretty slender by today's standard, but this was the sort of thing that you could do with pre-stress piling, unlike other, say, precast concrete piling that was around at the time, but pre-stress piling, much more efficient and certainly better for marine applications because of the control of cracking. Go to Hawaii, one of the, an early use, again, of deep foundations. There was this two-story parking garage at the Ala Moana Center. You may have driven by it or shopped there in Honolulu. This is an early, this is before BIM, so you see the little plastic car models and stuff. This is these are the tools of the day. But the idea was you drive piling and then you could cast a pile extension, and it was very efficient and quick, saved a contractor a lot of money. They tried to negotiate a fee that was 10% of the savings. I don't think that worked out, but you know, you don't ask, don't get, you know, right? So, and then Bob mentioned the Seattle monorail in 1961, and I understand that some of you went to Space Needle last night, so maybe you rode on this system. But at the time, you know, for ride quality, for a monorail, you can't have straight beams, you need curved beams. And so this shows one of those curved beams being set in place, this post-tensioned beam. And there were lots of arguments, I understand, this was before my time, but a lot of arguments about the free body diagram and would it work or it'll destroy itself when you PT it. But you know what? If you believe that a concrete arch works under the pre-stressing load of gravity, this is just the same thing turned sideways. So if you draw the free body, it actually works, and it's still there. In fact, this shows the erection of some of those piers, 62 or late 61. It was a temporary structure. There are actually deep foundations that are beneath this, and the piers are bolted down to the top of this plinth. And the idea was you could unbolt it and take it down. It was only a temporary structure. And so I think we can all attest it's still there, still operating, still unique structure. Bob also mentioned hollow piles. This shows some of the hollow piling coming out of the plant. You can see the inner hollow element. That the way this was done was, you see this pre-stressed line to the right of the slide. It's a form that's open. We're going to put concrete in, and I'll show you how this works in just a second. But you pull, you've got the pre-tensioning, then you pull a mandrel through the form as you pour the concrete. You can see one of the Seattle monorail beams off to the left there too. So they were doing a lot of different things. And one thing that fascinated me of this photo is you look around, there are a lot of the plant, most of the plant's pre-stressed concrete elements that these guys designed, built, put up, and said, you know, look what we can do here. It's pretty cool. This shows production of some of those hollow piles where the mandrel that Bob spoke of is being withdrawn as the concrete is placed. So it's really low slump concrete. There are vibrators on the inside of the mandrel, and as that gets pulled out by basically just a tugger, the inner hole is formed in the hollow pile, so you don't have to go in and wreck out a form or leave stay-in-place forms. Bob was the one that, he's the person that came up with this. This is these are drawings from the patent application. It was patented in 1964. Down at the bottom on the right, you can see the concrete, the low slump there with the mandrel being withdrawn. So it was a very clever idea, required just the right speed. If the tension in the cable got too high, you were going too slow. If it was too low, you're going too fast. You'll have problems, have to rebuild the pile. Having the right mix design, water content in the aggregate, all this stuff, pretty critical. They did a lot of testing to figure out how to make this work. My understanding is a lot of people tried to copy this, and I'm not sure that there was anyone other than, I believe the Japanese were able to come up with a system that worked. And I think Bob helped them with it. But it required a lot of grit, as we would call it today, of sticking with it to figure out the process. And of course, the advantage is they're easy to transport, or easier, they're lighter. And this enabled a lot of construction in the early 60s in the interstate program here. This is the Puyallup River Bridge here just south of, well, down Tacoma. Also, the approaches to the old 520 bridge and I-5 over Ravenna, just north of the U District here, were built using these. Of course, today we know there's some problems seismically with these, and we're retrofitting or taking some of these out. It was not known at the time, but these piles, this hollow pile did enable construction that was not otherwise very easy to do. And another interesting use of this same hollow pile technology, many people are not aware of, but Lake Washington was getting quite polluted with septic systems. And so there was an interceptor sewer that's built just below the water level that the sewer systems now connect into and take the outfall to the water treatment, sewage treatment plant. But this is another use of the hollow piling, and actually what today we would call accelerated bridge construction. So you've got piling that's driven below the lake level, caps, precast caps that were used, and then these were set on top and hooked together with, you can see some of the square connecting pieces there in the middle of foreground. And so this was all done underwater. So they're doing accelerated bridge construction underwater. I mean, who's doing that now? You know, it's pretty cool. I would say these guys were remarkably innovative. Here's another use, replacement of a bridge, Scatter Creek. This is on Highway 410 down in Enumclaw, so a little southeast of here, was a washout from a huge flood event. You see the Highway 410 bridge in the background. The bridge in the foreground was Weyerhaeuser's haul road, which had been a railroad and replaced by trucks, and Weyerhaeuser liked to run their trucks way, way over load limit. So there was no way they were going to be out on the highway. So they had this parallel haul road. Well, Concrete Tech with, again, some of this piling technology, pre-stressed concrete piling. You can see the backstays that react the pier, which will pivot out. I'll show you another photo in just a second of a similar structure. This was replaced in 6 weeks from the time the bridge washed out. And the US 410 bridge took a year to replace. So Weyerhaeuser had their bridge and their haul road back in operation pretty quickly. Here's a similar type of structure with this canted leg approach. This was in some rock over in on the Salix River on the Olympic Peninsula. And this bridge was erected not with the conventional cranes you drive up the forest roads, but high lead logging equipment. So the loggers were like, yeah, piles, concrete, wood, we don't care. So you can see the high lead equipment in the middle upper part of the photograph. Then eventually, in the late 60s, early 70s, Walt Disney World in Florida was built in Orlando. They wanted a monorail. They'd had a monorail down in Anaheim, which the curved pieces of that were normal reinforced concrete, and they sagged like crazy. So they wanted to use this curved beam technology, and so that was used in Walt Disney World. This shows kind of a rendering of how that system went together with a double guideway at the top, hung off a steel torsion beam. This allows the girders to rotate at the end without putting load into the column. Again, this is accelerated bridge construction. See the deep foundations below, and this was a cast-in-place cap, but the column was grouted into that cap. This was all made in Washington. Nobody could build those beams except for, at that time, except for Concrete Tech. So every one of the beams in the original Walt Disney World system, the Magic Kingdom, were shipped all the way across the country by rail. A little bit later in the 80s, just kind of moving ahead here, another use of pre-stressed concrete piling. This was to lightly pre-stress the concrete, so sort of partially pre-stressed concrete. And you could load it laterally. You didn't yield the strand, and it would pop right back. So this became a replacement for timber fender piling in a lot of our marine structures. Timber fender piles have a problem of deteriorating, getting the whalers get broken by impact, that sort of thing. And so many of the more heavy-duty piers now, both commercial and Navy, use these this pre-stressed fender pile concept. So still in use today. This was just the brainchild of these same guys. How can we use pre-stressed concrete a little differently? Continuing on in closer to today, this was a precast. This is a drill shaft foundation. This is the Getty Center down in LA, but a precast concrete cap. You can see this coming back as, again, accelerated bridge construction with guideways. This particular design was like a Swiss watch going together, and this was the contractor's idea to do this, so they owned all the tolerances. And it's amazing when they come up with the idea of what they can put together. If we design engineers had come up with this, they probably told us 100 times you can't do that. But remember how I started the presentation here is, yeah, maybe you can do it. And even today, this was a more recent project that we were involved with, Highways for Life, a federal highways project for a complete precast bent system for high seismic regions. WashDOT built a demonstration bridge using this concept down on I-5 south of Olympia. These columns have been used in some other bridges over by Microsoft, and we've extended this to deep foundations again with, this is the 520 bridge. This is the bent that supports a transition span to the floating structure, precast bent on the drill shafts that they used for the 520 replacement. And then finally, this is just a rendering of a bridge that replaced the old bridge over the mouth of the Cedar River at the Boeing Renton plant. So every 737 that rolls out of that plant, and I know they're kind of stacking up right now, but every one that rolls out of that plant goes over this bridge. So there was a definitive notion that they wanted this bridge that was there replaced quickly. So this uses the precast bent concept, and those precast columns I showed you in the previous slide now married up with drill shafts that we had tested at the University of Washington, showed this works. And so the conclusion here, just this quick tour of the 60 years and the legacy of Art and Tom and Bob and even Hal Birkeland, is that you know, it was an innovative concept, pre-stressed concrete to start with. Today, it is a workhorse of our infrastructure, marine, transportation, building, you name it. It's cost effective, got really good quality control, and as long as we're putting our brains to it and continue to solve some of the problems that, you know, invariably come up, we are forging ahead with some really nicely innovative things in the industry. So I would offer that innovation fits really nicely with the Ben Gerwick Award and the concept behind that award. And so on behalf of all the principals of the original ABAM, the two Anderson brothers, Art and Tom, Bob Mast and Hal Birkeland, I thank you for your attention.
Okay, so I think Lee did a good job of getting across the innovativeness coming from the Andersons. Just want everyone to realize Bob's family, the Mast family, is sitting here in the front row. His lovely wife Marilyn and the rest of the gang, and they're all here to cheer him on. Well, thank you, everyone. I don't know if anybody has a question or anything that you might be interested in otherwise. If not, then thank you for coming, and the next session will begin in 10 minutes. Okay. Take another photo. Okay.